Hello, today we want to present to you about ODE application videography. And this is our team members, Irene, Radin, Danish, Asrul and Aidil.
What is an ODE? ODE is a mathematical equation involving a function and its derivative. It also describes how a quantity changes with respect to time or another variable. For the importance of ODEs in engineering, it can model real-world dynamic system. It also can predict system behavior over time. Other than that, it can assist in analysis, design and optimization. There are two real-life applications. The first is disease spread among university students, and second is water distribution storage tank.
For problem 1, spread of a virus in a population. For problem statement, a university wants to predict how a contagious disease spreads among students, so preventive measures can be planned. For real-world applications, first, hospital resources planning. Engineers and healthcare administrators use disease spread models to estimate the number of future patients. Second, smart city and public transportation system. Transportation engineers use infection models to study how diseases spread through crowded buses, trains, and stations. Last, biomedical engineering. Biomedical engineers develop computer simulation that predict disease transmission and evaluate the effectiveness of vaccination programs. For the assumptions, the population is close and no immigration or emigration occurs. All individuals mix uniformly and every person has an equal chance of meeting any other person. Resources and susceptible individuals are limited. The disease cannot infect more people than the population size. The infection rate is proportional to the current number of infected individuals, and more infected people means more opportunities for transmission. Recovery, death, and mutation effects are neglected. Now, moving on to ODE formulation. P function is the number of infected students at time t, which is days. For logistic ODE, dp over dt equal to kp multiplied by 1 minus p over m. K means infection spread constant, m total student population, which is maximum possible infected. For meaning of each term, for kp represent disease spread, 1 minus p over m represent limitation of available people to infect.
Solution for the problem 1. This is the logistic ODE equation where P is the infected population, K is the growth rate, and M is the carrying capacity, which is the maximum population. To solve the ODE, we first need to separate the variables. Now, we need to simplify it. And finally, multiply out. Next, we need to factor out 1 over M, so the equation becomes this. Next step is to do partial fraction decomposition. We need to find the value A and also B. We found that A is equals to 1 and B is equals to 1. So, we substitute back the value in the equation. Next, we need to integrate both sides. After that, we get this, and we need to exponentiate both sides. After that, we get this, and we need to put it in standard form. And finally, we will get the logistic growth equation, which is this. Example calculation. Therefore, we got the total campus population, which is 1000. Initial affected, P0 is equals to 10, and the growth constant K will be equal to 0.25. Next, we first need to find the value A to complete the equation. At t is equal to 0, A is equal to 99, and we will get this equation. This equation is useful to do the next one. Prediction after 10 days, P10 will be equals to 110, while prediction after 20 days, P20 will be equal to 599.
For the problem 2 is water tank model. My portion of the talk will cover the critical assumption we must make to model it and the step-by-step mathematical formulation of our governing ODE. Once the mathematical setup is complete, I will hand it over to my teammate who will walk you through the integration and analytical solution. The problem statement is modern water distribution system face the critical challenge of maintaining stable hydraulic pressure while managing fluctuating consumer demand. Next, we will go to real-world application. In municipal supply, maintaining constant pressure for residential areas to ensure reliable water access at all hours. For industrial facilities, the cooling and processing system that requires a high precision and volume of water to operate safely. And lastly, in emergency reserve, engineering fire hydrant system have guaranteed head pressure during peak emergency event. To build a reliable and solvable mathematical model, we apply 4 core engineering assumptions. First, both inflow and outflow are assumed steady over the observation period. Second, the flow density is uniform and there is no significant sloshing or turbulence at the surface. Third, the cross-sectional area remains constant across the entire head of the tank. And last, water density is constant, allowing us to model change in volume directly as change in mass. So next, we will go to the ODE formulation. In an open system like a water tank, the rate of accumulation is the difference between input and output. So, we will get dV over dt equal to Q in minus Q out. After that, we will relating volume to water level. For a cylindrical tank, volume is expressed as the product of area and head, V equal to A to H. After that, we will differentiate with respect to time t, where A is constant. A dH over dt equal to Q in minus Q out. And after we move A, we will get dH over dt equal to Q in minus Q out over A.
Now, let's apply actual physical constraint to this mathematical framework to solve a practical problem. The scenario:
To solve this problem, step first is substitute the constant into the general ODE using our formulated equation from part 1. dH per dt equal to 0.08 tolak 0.05 over 10 and dH over dt is 0.003 meter per second. Because Q in more than Q out, the derivative is positive. This tells us the water level is rising at a constant rate of 0.03 meters every second. Second step is solve the equation via separation of variable. Move dt to the right side to separate your variable. Integrate both sides of the expression. And third step is evaluate the integration constant C. Apply the boundary initial condition at t equal to 0 and hash 0 equal to 2 meter. Plugging C back in gives us the specific predictive formula, which is hash t equal to 0.03t plus 2. Next step is calculate the final water level, which is the water height after 1 minute is hash 60 equal to 0.03 in bracket 60 plus 2.0, and the answer is 2.18 meter. For the reflection session, I will explain 4 important values gained from learning differential modeling in engineering. First is relevance of mathematics. Mathematics help engineers convert complex universe system into a measurable and understandable data. It also allows engineers to predict physical behavior accurately and become the foundation of engineering analysis and design. Second is critical thinking. Differential modeling encourages engineers to think critically and solve problems from the beginning instead of only using formulas directly. This also helps balance mathematical theory with real-world application. Third is technological adaptability. Modern engineering software and computational tools are built on mathematical principles such as ODE calculus. By understanding the mathematics behind the technology, engineers can learn new tools more easily and adapt quickly. Lastly is lifelong learning. Differential modeling develops strong and lasting problem-solving skills. Engineers will face many new and unfamiliar challenges throughout their careers. In conclusion, ordinary differential equations are essential tools that help engineers understand, predict and solve complex real-world problems. By applying this mathematical model, engineers can create safer, smarter and more efficient systems for society.